In today's lecture on mathematical structures, we're going to be looking at groups. In the very first lecture, we looked at structures called magmas. And in the context of that lecture, we also introduced a notion of a semigroup and a notion of a monoid. But I don't think we touched on groups, which are simply special kinds of monoids. But instead of starting from monoids, we're going to start more from almost like the real life scenario which motivates the notion of a group. And then we're going to link later, once we try to formalize this real life scenario, we're going to link it up with monoids. One of the important notions in life is the notion of symmetry. And just as with anything in mathematics, in mathematics we kind of discretize the universe, right? We think of universe in terms of a set of points, maybe. So if we take a discrete picture and try to talk about the symmetry of that picture, this is where the notion of a group will emerge. Okay, so let's look at a specific example of such a picture. Consider the following drawing. Looking at this drawing, we clearly see that this drawing has a certain symmetry to it, right? Now, the symmetry that this drawing has to it might be a bit different from the symmetry that the other drawing has. And let me make the other drawing. And then let me make a third drawing as well. And let's try to talk about whether any of these drawings appears to be more symmetric than the others. So we have three drawings here, A, B, and C. Would you say, okay, first of all, imagine a kind of ideal version of these drawings where the intended symmetry that you might notice is actually fulfilled. And then with that agreement, which of these three drawings would you say that it has more symmetry than the others? And maybe we can order it in that order. So the one that has most symmetry, the one that has less symmetry, and the one that has least symmetry. Okay, I see in the chat that there is a proposal that A has most symmetry and C has least, with B being in between. Would you be able to explain what you mean by that? In which sense does A has most symmetry? Okay, so the reason written out there in chat is that so Chad says that he can see more ways of x's that he can get to produce this butterfly kind of folding. Let's draw some of these x's. So we have, here is one axis, here is another one. For the second drawing, I think we only have one for the second drawing. And for the third drawing, we have none. So indeed, in terms of judging in terms of this number of x's, it seems like A is most symmetric than C. But certainly there is some symmetry to C as well. You wouldn't say that C is completely lacking any kind of symmetry. I mean, I can draw something that will completely lack any kind of symmetry. For instance, something like this. Now, this would be a thing which might entirely lack any kind of symmetry. But certainly C is better than that. But we don't have x's in either case, C or D. So is there something more than just about the axis of symmetry? Is there other kinds of symmetry, perhaps, which we still need to identify in order to get a full picture of the symmetry?
Afternoon, Prof. We can also have rotational symmetries as well.
That's right. We can have rotational symmetries as well. And if we look at picture A, we could rotate a picture A by 90 degrees wouldn't be good enough, right? But we can rotate by 180 degrees, and that would be fine. What about picture B? We could do the same thing there, right? Imagining that my drawing was perfect, which it isn't. And this is exactly the kind of symmetry that C has, but A and B do not. And with D, we have complete lack of any kind of symmetry. So there seems to be two kinds of symmetries. One is about the axis and the other is about rotation. But in fact, even the axis is also some kind of transformation, right? So Chad was talking about this butterfly effect. So the first step to the first insight to have here is that symmetry is an action that we can perform. And to make explicit what actions we're performing, we actually could discretize these pictures, as I promised in the beginning. We could take just a sketch of these pictures given by just a few points, and then we can talk about the performance of a certain action as a function from the set to itself. So for the first picture, I'm going to choose, let me see, maybe the choice I'm going to make will not be the most efficient one. Please forgive me for that. Now imagine I had a shape which consists of just the red dots. So it's basically a graph. But we actually want to keep track of the distance between these points. So between every two red points, there is a certain distance, which I can measure by drawing a straight line and then seeing how long that straight line is. And then I could ask for a function. So let's label these points first. Let this be A1, A2, A3, A4, A5, and A6. So I could ask for a function from the set of these A's to the same set but the function shouldn't be just arbitrary. It should preserve the distances between the points. So the distance between AI and AJ must always equal to the distance between f of AI and f of AJ. And then I could do the same thing with the other drawings as well, where I first, of course, will have to produce these discrete versions of the drawings by showing the points. Would anyone like to give me a suggestion? Maybe I could have used less points than I'm using to express the same idea. So here I need to take care that I would probably need something like that. Yeah, I don't think I'm able to follow the comments here from you, Chad. You posted 3 comments. You were saying something about B. I'm not sure I understand what you're saying about B, about the drawing B. I don't think there is an additional folding symmetry that we haven't displayed yet. If you think there is, you could maybe clarify. Then your second comment is about the horn on the left, where inverted then it would work, but you'd lose the rotational symmetry. Yeah, we don't want to lose anything, so that's fine. And then why I haven't labeled the basis on the triangles for A? I don't understand what that means. You're saying that the folding symmetry we have for B is incorrect, and I completely agree with you. We made a mistake there. This folding symmetry is incorrect, right? So in fact, B and C are quite similar to each other in that, right?
Prof, I think with regards to his comment with diagram A, he means the point between A2 and A3 and A5 and A4, those ones. Is there any particular reason we haven't labeled those? So either in diagram A and also B, you could also make the same argument with respect to the
Yeah,
other
we
diagrams
could.
as well.
Yeah, that's a good point. We could have labeled all the corners. I was just trying to use minimal labeling so that the symmetries are the same. But I think even in this case, I could have just chosen one point there and one point here, and it would still remain the same. But let us first, yes, so thank you very much for that contribution. Let us first try to fix what I messed up here with B, right? I said something terribly wrong about B. Let's try to have a picture. What should the correct picture be so that we have perhaps a rotational and one other symmetry? And I think Chad already suggested what it should be. I think he was suggesting to, okay, but then the rotational symmetry will be lost. That was what he was saying. No. So we want a picture with two of them, and then one for C and then none for D, which we already have. What would be a good picture with having just two symmetries? So there is a suggestion to copy what was on the left on the right, and copy what was on the right on the left. Not sure I agree with that. If we do that, then we will also have okay, I think we just need to maybe shift things up a little bit. So what we could do probably, so thanks for that suggestion, but I think we should implement it a little bit like this. So maybe we, just to keep things simple, maybe we draw these ones right here. Then we have this axis there, but we no longer have the horizontal axis. But we also don't have the rotation, right? Okay, I really need your help now. I'm quite stuck here. We want a picture that will have only two of these three symmetries. Maybe it's not possible. Who knows? Maybe it's not possible, huh? Or is it possible or not? Let's think about it a little bit more. Mm-hmm. Okay, so I mean, it might turn out that some possibilities are not possible. So let's make our question a bit more specific. Let's choose two specific symmetries which we would want to retain, and then eliminate the third one. And I think the way we had it originally, the one that was not quite correct, but the way we had it originally was that we were retaining that vertical line and the rotation. So let's try to make a drawing that would retain these two symmetries, but would eliminate the third one. So one way of eliminating the third one and this is where we come to the point where we might be thinking, okay, is that possible, right? Maybe we can get the vertical flip by a combination of the flip this way, and 180-degree rotation. Maybe that can determine the flip that way. Yeah? Great. So we've now come to the heart of the matter, which is to think of symmetry as an action, and then to try to figure out when can certain action be decomposed into other actions. So let's remember this problem we encountered here. Once we will introduce the idea of a group, then we will be able to see how that idea will help us to actually solve the question here. So symmetry becomes an action, as we agreed, and we can think of this action as a function, and it could have been the function from the entire white set to itself, or just its discrete version. In this case, the discrete version is good enough for representing the symmetries that we're exhibiting here. And then we require that this function must preserve distances. Now, if the function preserves distances, then it will have a certain property. It will be a bijection. Why is that? So we take a special case of this equality, the preservation of distances equality. The special case where the 2 points that we're measuring distance between are different, are the same point, or rather where the values are the same. And so we get that if f of ai equals f of aj, right? Then we get that the distance between ai and aj must be equal to the distance between these two equal things. But of course, the distance between two equal things is 0, so the distance must be 0. The distance being 0 implies that ai equals aj, right? So a symmetry is always an injective function, or an injection. But because we've got a finite set here, an injection from a finite set to itself will always be a bijection. And hence a bijection. In the case of finite discretization. A more general idea, kind of generalizing from the specific picture, a more general idea is to regard any bijection as a symmetry. In fact, you can try maybe on your own to have any bijection. I mean, it wouldn't be difficult to have any bijection in between from a set to itself, from a finite set to itself, and then you can draw distances in such a way that this bijection becomes a symmetry, and that's not difficult to do. You just take this higher dimensional tetrahedron, right? So imagine, let's say on an example, maybe I'll first make the claim. In fact, any bijection can be so any bijection from a finite set to itself let me now switch to calling the elements of this finite set simply natural numbers. Can be thought of a symmetry simply because you could take, so I will illustrate in the case of n being equal to 3. When n is equal to 3, or maybe 4 rather, you could consider this tetrahedron, right? That has this 4 points displayed in a three-dimensional shape like this. So this is actually the front side of the shape. It's called a tetrahedron, and there's one back side there. And the idea is that all sides are of equal distance. And then, because all sides are of equal distance, then any bijection would actually preserve this distance. But you definitely do need a bijection because of this observation that if it preserves distance, it must be a bijection. With the number being n, to implement this, you would need an n-dimensional space. But we are mathematicians. As mathematicians, we are fine with n-dimensional space. Okay, so the first step is realizing that a symmetry is some kind of bijection from a set to itself. And the second step is that the symmetry seen as an action, which corresponds to the bijection, which kind of bijection is the is when we formalize the idea of, for instance, taking the shape and doing something with it, either folding or rotating and so on. But then when you have two actions, you can perform one and then the other, right? Like, for example, here we had two actions. One is flipping along this vertical axis, and the other is rotating by 180 degrees. And we know that by these two actions, the shape matches onto itself. So these two functions preserve distances. But of course, if two functions preserve distances, then their composition will also preserve distances, right? So if you've got the functions f and g, so if f and g are symmetries for the same shape, which means that that set over which on which there are bijections, that set has some distance function associated to it, so it represents the kind of the discrete version of the geometry of the shape. And then being symmetries for that shape simply means that the functions preserve the distance. So if both of them preserve, then their composite will also preserve, right? And it's not difficult to see that. So the distance from okay, let me first finish the sentence. So both F and G are bijections on the same set, and both preserve distances. Then their composite will also be such. Why? Well, it's not difficult to see why. So the distance from AI, let's say, and AJ, between AI and J, will equal to the distance between FAI and FAJ, because F is a symmetry, because F preserves this distance. And then that will further equal to the distance between G of F of AI and G of F of AJ, because G preserves distances, right? So overall, of course, we get this is nothing other than G composed with F applied to AI and G composed with F applied to AJ. So that's how we get that composing symmetries, we still get a symmetry. And in other words, that means that whatever symmetries you got there, right, their composites are also symmetries. And so this composition for a given shape, the composition on symmetries gives us, in fact, a monoid structure. Why a monoid structure? Because composition is associative, and we always have the kind of basic symmetry of mapping everything to itself that clearly preserves distance, right? So symmetries form a monoid. They form a monoid, and I'm now talking about symmetries of a given shape, right? Where one is the identity function, it maps every AI to itself, and multiplication of the monoid is the composition of symmetries. But they not only form a monoid, they form something a bit more than just a monoid, because since each of them must be a bijection, we can reverse the process as well. So if I go back to this picture, think of rotation by 180 degrees in this direction, right? That's one symmetry, but it has a kind of opposite, which is rotation by 100 degrees the other way around. Or if you like, kind of going backwards that way. Sorry, this drawing that I made here, I'm not very good at symmetries today. This green arrow would be exactly the same rotation, right? The opposite one would be going backwards this way. With the flipping, again, so we can flip this way or you can flip backwards. But of course, with the flips, it's interesting that with the flips, the bijection and its inverse would coincide. So not with the rotation, but with inverse, they do. In fact, with this rotation by 180 degrees, they also coincide, right? That's why my two pictures were actually both good. If you rotate by 180 degrees once and then the same second time, you will get back to original state. So the inverse of 180-degree rotation is itself. There is also 90-degree rotation, which in this specific example we don't have, but we could have other examples where we have that, and there the inverse would not be itself. But in any case, whether inverse is itself or not, we have inverses. And this is what a group is. A group is a monoid where for each x in M, there exists something we write x minus 1, such that x times x minus 1 equals to 1, and x minus 1 times x equals to 1 as well. Okay, there is another question that came through on chat from Chad. Once A is folded, is the distance from the far point on the left and the far point on the right if that distance isn't 0? So what is distance between f of A2 and f of A5? So it depends which folding we're doing. No, folding is not the right way of thinking about it, Chad. We're not folding it, we're flipping it rather. That's basically what folding is, to flip. So the axis of, if you consider the axis of flipping, then you can imagine that you're folding along that axis. But in a general picture, we don't have axis. We just have abstract point and distance between them. So we don't want to think in terms of folding, rather in terms of flipping. You can think of flipping as a rotation if you allow yourself to go in the third dimension. So it's not rotation on the plane, it's a rotation in the dimension that goes out from the plane where we are in. It's like the two hands. So the two hands on our body, right? We can't get one from the other. Remember, these are 3D objects, right? And we can't get one from the other by rotation. They will never match. The left and right hand will never match. But we can get them by flipping. But if we allow to go in a higher dimension, then there we could should be able to find a suitable rotation that will allow us to match. Just like here, flipping along any of these axes cannot be represented as rotation on the plane, but it can be represented as rotation which leaves the plane. Yeah. Okay, great. So that's what a group is. A group is a monoid where every element has an inverse. And of course, we know that for functions, having an inverse is equivalent to being a bijection. And so this is how we capture the idea that it should be a bijection. I mean, that every symmetry should be a bijection. And then, as we remarked earlier, individual symmetry can always be seen as, I mean, every individual bijection can always be seen as some sort of symmetry. But with a picture like this, which makes an arbitrary bijection to indeed be a symmetry, with a picture like this, if now our shape is this, then every other bijection will also be a symmetry. So one then comes up with the following question. And to be honest, I actually do not know the answer to this question. I don't even know if the answer to this question is known or not. Is every finite group the group of symmetries of a certain shape? The way that we've defined this. And of course, when we talk about shape, we're not restricting the dimension. So before we know the answer to this question, for us, symmetries only provide examples of groups. And then you just abstract away from there. You say, okay, now let's consider an arbitrary group as a generalization of symmetry. I don't see how this is a detour into category theory, Chad. Okay, so now that we've motivated the notion of a group in a very specific way, of course, there are many other groups that are very important that are not necessarily linked with symmetry per se. So first of all, we have groups of symmetry. And then we have many other groups, like, for example, the group of integers, with plus being our operation and 1 being our identity element. So this monoid is also a group where the inverse of an element is minus that element. So x plus minus x equals 0 here. Okay, I'm making too many mistakes today. I should say 0 there instead of 1. And then we have another interesting group is the, let's say, the positive reals, where operation is multiplication, and identity element is 1. There, of course, inverses are usual ones, and so on. When we looked at monoids, we had this, we motivated the notion of a monoid using this representation theorem. We said that every monoid, so let's just recall that if I have a monoid M, it can be represented as it can be inserted into the functions of, into the monoid of functions of M. We call this map R. In fact, we started with a general magma and we build a certain R and then asking for that R to preserve the operation gave us the axioms of the monoid. So the same representation works here. We can represent every group. So every group G has an injective operation preserving map to the group of all symmetries, let's say, all symmetries on a given set. So this would be all bijections. Those endo functions f from G to G, which are bijections. This map is given by exactly the same way as this other one was. In fact, it's the same map. Mapping G to the function from G to G, which maps x to G times x. Why is this theorem important? Because, I mean, while we might not know whether every finite group is the group of symmetries of a certain shape or not, we do know that this specific group, the group of all bijections from a finite set to itself, that one is the group of symmetries of a certain shape, namely a tetrahedron, which has the same dimension as the number of elements in G, right? And so by this injective function, we're kind of representing our group as some portion of the group of symmetries of that higher dimensional tetrahedron. The theorem is actually a consequence of the same fact for monoids. You start with G as your monoid, and then we know that. So maybe it's worth writing out. G as a monoid has a representation going from G to endo functions on G, right? But now you want you don't want to go to endo functions. You want to go to bijections, not just all endo functions, right? But the thing is that this representation is actually the same one as before, if you recall that from last time. So it maps G to a function that maps every x to G times x. And then one just realizes that, okay, we already know that this map is injective. This is something that we would have remarked in the first lecture, and if we didn't, it's not difficult to see that it's injective. Since, let's maybe make this remark, this map is injective since if so let's call this function something. So let's call this thing R with subscript G, as I think we did last time. If RG equals RG prime, right? If these are the same map, then they must have the same values. Then RG, and specifically they must have the same value at x equal 1. So that RG at 1 will be equal to RG prime at 1. But what is RG at 1? RG at 1 is G times 1, which is nothing other than G. And RG prime at 1 is G prime times 1, which is nothing other than G prime. So that's how we get that the map is injective. G ends up being equal to G prime. Now, so okay, so we know it's injective. We know it preserves we know from lecture 1 that so let's call this map R as we did before, that R preserves the monoid multiplication. Where, of course, and G is seen as a monoid under composition of functions. So what remains to prove is then the following. So basically, we already have the map we're looking for. It's just that it points us to the wrong spot. We don't want to go to all possible end functions of G. We want to go to specifically bijections on G, right? So what remains to prove is that firstly, each RG is actually a bijection. And secondly, the map R preserves the inverses as well. So we do know that R preserves, from lecture 1, we know that R preserves the monoid multiplication. Not only that, we know that it preserves a monoid identity element. At least I'm not sure now if we actually prove that or not. But it's not difficult to see that it does preserve identity element, because imagine if G is identity element of the monoid of the group G, then the function will be mapping x to 1 times x, and of course that's the function mapping x to itself, and that's the identity function, which is the identity element for the composition of functions. And then we would want R to preserve the inverses as well. Why would we want that? Because we said in the theorem that this is an operation preserving thing. But by operation, we didn't mean just the operation of multiplication. We also meant the other operation that the group has. And maybe this is a good point to go back to here and make a remark that in a group, we have an additional operation, the operation of taking an inverse of an element. Which maps, so it's the operation that maps x to x inverse. And so when we were talking about operation preserving here, we meant, maybe I should have said, sorry, I should have said structure preserving, and that would mean preserving all operations in the structure. So preserving the binary operation of multiplication, the unary operation of inverses, of taking inverses, and there is a third operation which we have already in a monoid. This is this one. This we think of as a nullary operation. So the arity of the operation, the so-called arity of the operation, is the number of inputs you need to get the output. So with a unary operation, you just need one thing, that's x, to create x minus 1. With a binary operation, you need 2, x and y, to create x times y. But to create one, you need nothing. So that's how this is seen as a nullary operation. So it preserves the unary operation of inverses and the nullary operation of identity. Now, because of this structural importance of groups, that there's a kind of extra piece of structure as emerging in a group, we sometimes write a group not as a triple, but as a quadruple. G dot 1 and this unary operation of taking the inverses. In a similar way, how when we switched from a semigroup to a monoid, right? A semigroup was defined as a set with a binary operation. Now, when a semigroup has an identity element, it is unique. So technically, we didn't have to specify this here because it's uniquely determined by multiplication, but nevertheless, we did specify it. And in the same way, although inverses in a group turn out to be uniquely determined, that's something we can still prove if we'll have time for that. Although they're uniquely determined by the rest of the structure, we still want to include it as part of the structure because we want our maps, structure preserving maps between groups to preserve not just the dot and the 1, but also to preserve the -1. And so we already know that this map R preserves the dot and the 1. That comes from the previous lecture. And if we didn't do the preservation of 1 specifically, then I explained it now and it should be fine. But we still have to establish that it preserves the unary operation of taking inverses. But you see, if it does preserve unary operation of taking inverses, right? Then it means that, I mean, because every element here has an inverse, every element on this side obtained from the left side will have an inverse as well, right? So what I'm saying here. So imagine we know that this is true, right? Then R of okay, let me use G. So if H, or rather G prime, is an inverse of G. Okay, let's put it this way. If R of G inverse equals R of G inverse, that is exactly preservation of inverses, right? This is equality establishes that R preserves inverse, specifically of G. Huh? But if this is true, then each R of G will be bijection, because it will mean that it has an inverse, right? If it has an inverse, then it's a bijection. But there is a problem here. And G is not a group, it's a monoid. So we actually don't have the operation of taking inverses on this side. We do have it here, because every bijection is an inverse, right? But we don't have it here. So we can't really talk about R preserving inverses in that sense, because we don't have a guarantee that R of G will actually have an inverse. So instead of saying that this R, the one that now ends up going to end G, not yet in sim G, that R, instead of saying that R must preserve the inverse unary operation of inverses, we will say that R preserves invertible elements. So we'll have to make it a bit more explicit, because we can't make use of the operation of unary operation on this set because it's not defined for all functions, right? So R preserves the inverses in the following sense. R of G times R of G inverse equals 1 equals R of G inverse times R of G. So think of R of G as your function. And now it's the function that corresponds to element G. And now this is the G inverse, the inverse of element G. And if this were to be inverse of RG, that means that this product is equal to 1 as well as the other product, right? But of course, this we have. This is trivially true, right? The second point follows from preservation of dot and 1. The simple calculation here is that, okay, this left-hand side here, because R preserves dot, is going to be equal to that, but G times G inverse is 1, so it's going to be equal to R of 1, but if R preserves 1, it means that is 1 as well, and in the same way we can go backwards, and we get here R of G minus 1 times R of G, and so the equality across has been established. But on the other hand, once we know that the map R preserves inverses, right, that does guarantee that each RG will now have an inverse. But now RG is a function which has two-sided inverse. That means it's a bijection, right? So this first point follows from the second one. First point is an immediate consequence of the second one. Okay, so once we find out that each RG is actually a bijection, this means that our function R, in fact, maps everything from G to a subset of end G, the subset of all bijections, right? So exactly it maps to sim G. And it's defined exactly the same way as it was requested to be defined, so that's fine. And then it does preserve all the structure because it preserves multiplication, it preserves identity, as we already remarked, and this guarantees us that it preserves inverses, which now at the level of sim G can be seen as preservation of the unary operation of taking the inverses. So what I'm trying to say here is that we proved the theory. So there is an interesting fact that kind of emerges from the last part of this proof, namely the observation that when R preserves multiplication and 1, it automatically is forced to preserve the inverses as well. In fact, something stronger is true. If a function f between two groups, so G and G prime, preserves I'm just looking at our previous notes. Yeah, we did define what a homomorphism of magmas was. So if a function f between two groups, G and G prime, is a magma homomorphism, is a magma homomorphism. In other words, this means that f of x times G equals f of x times f of x times y equals f of x times f of y for all xy. then, so if it preserves multiplication, then it will preserve 1 as well. Then f preserves 1 and -1 as well. What that means is, of course, that f of 1 will equal to 1 on the other side, and f of x minus 1 will equal to f of x minus 1 on the other side. So f of 1 equals 1, and f of x minus 1 equals f of x and the minus 1 of that for all x in G. So we already kind of saw, we almost saw the argument for how we get preservation of this once we have that and that together. But now it turns out we can even get that out of just that. So let's see how that's done. Maybe I will need some help here. Okay, so let's first prove this one. We want to get f of 1 to equal to 1, right? How can we get that to happen? The only thing we know is that f preserves multiplication. Any ideas? Maybe this is how we can get this to happen. F of 1 equals f of 1 times 1. Surely you will agree with that. 1 is equal to 1 times 1. But because f preserves multiplication, this equals to f of 1 times f of 1, right? But remember, f of 1 lives inside a group. So the same statement would not be true if G prime were not a group. Okay, it will make use of the fact that G prime is a group. So we couldn't actually infer preservation of monad identity already at this level, at the level we were here, simply because that one wasn't a group. So there we did need this as a separate a piece of knowledge. But once we know already that we're going into a group, then preservation of identity is a consequence of preservation of multiplication. And so once we have this, what we do, of course, here is, any suggestions? What do we do here? How do we get from here that f of 1 equals 1?
Doesn't it follow directly from the group?
Sorry, could you please say it louder?
Does it not follow directly from the group axioms that the statement holds precisely when f of 1 is the identity?
So how does it follow from group axioms?
All right, one of the group axioms requires the existence of an element such that if you multiply it with any other element, you get that same element back. So we see that f of 1 actually acts as such an element. So we must infer that it is the identity.
I'm not sure I follow there, because I mean, how do you know that f of 1 multiplied by anything else will be that thing? Here we only know that f of 1 multiplied specifically by f of 1 is f of 1. We don't know that f of 1 multiplied by every other thing still gives back that other thing. In fact, we've seen already a few times monoids where you have some element equal to that element multiplied by itself. Here's an example. In the monoid of the power set of a set, where the operation is intersection, and an identity element will be the entire set. In this monoid, A intersected with A equals A. So that doesn't guarantee that A is an identity element. That is true for every A. Yeah? So the question still remains how to infer from here that f of 1 equals 1. Any thoughts?
If you take the inverse of f of 1 on both sides, then you have 1 is equal to f of 1, or the identity element is.
What do you mean by taking the inverse of f of 1 on both sides?
The f of 1 to the power of -1.
So you're suggesting I should do this?
No, so I'll multiply both sides by the
That's
inverse
right.
of f.
Yeah, that's right. Yeah, thank you very much, Dan. So we multiply both sides by the inverse of f of 1. Then on the left side, we'll get f of 1 times that. On the right side, we'll get that. Of course, because the operation is associative, I don't need to worry about the brackets here. And then on the left side, we get 1. And here, these two give us 1. So we get f of 1 times 1, which then gives us f of 1. So that's how we prove that f of 1 is equal to 1. And once we know that f of 1 is equal to 1, after that, the other one is not difficult to prove. Because f of x times f of x minus 1 equals f of x times x minus 1. That equals f of 1. That equals 1 from what we already proved. And so also the other way around, also f of x minus 1 times f of x by a similar argument equals 1. But we don't know yet necessarily that this is going to be the inverse, but it actually turns out another general fact that inverses are always unique in a group, something we haven't proved yet. Element having these two properties uniquely determines this thing. If we knew that, then we could say, okay, now we know that this must be the inverse because f of x can only have one inverse. We don't know that yet, so we still have to kind of implicitly insert that proof in this proof. So let's see how we can do that. I think we can just multiply by, we just take one of these equations, in fact, and we multiply both sides by the actual inverse of f of x on the left side, perhaps. So so we actually don't need the other equation. The first, the one will be sufficient. We take f of x inverse, which we know exists. We multiply that by this whole thing. And that gives us that it equals to that. Of course, the left side here, because these two together will give us 1, and then 1 times that will give us, so it's 1 times that, which gives us that. And on the right side, we had that thing times 1, which of course is just f of x inverse. And so that's how we get eventually that these two things are equal. Okay, there we go. And then the proof is complete. So that's a nice thing about groups, that it's sufficient to preserve the group multiplication, and then the rest gets automatically preserved, the rest of the structure. It's something very unique about groups, which is in general not true for monoids. For example, preservation of multiplication does not guarantee preservation of the identity element. I'm not going to go into the example for this now, but you might want to come up with an example of your own. Okay, maybe it's a good idea now to go back to the problem we encountered here and try to answer that question. So the question basically was whether flipping in this direction and 180-degree rotation can be used to describe flipping in that direction. And we could perhaps model this question on a simple example where we take just 3 points, form a triangle. Remember, triangle with all sides being equal, that's the situation where any bijection will turn out to be a symmetry, right? If I go back to this picture, that's exactly the kind of model we have for arbitrary bijections turning out to be a symmetry. So let's stick in this world of arbitrary bijections on a 3-element set, and then we could describe each of these 2 maps. So if this is the bijection, let's just label these as 1, 2, 3, and so the flipping along the axis that's shown will be a bijection which will do what with 1, 2, 3. So it will map 1 to 3. It will map 2. It will keep 2 at the same spot. It will map 3 to back to 1, right? And then what about rotation? So what does rotation do by 180 degrees? Well, we can't rotate this one by 180 degrees. Again, I'm talking nonsense here. So maybe we need to turn this picture into something like this. So we have a 4th element. The 4th element again still stays the same by the flipping, and by 180 rotation, what happens there? Everything moves to its opposite side, right? So 1 moves to 3, 2 moves to 4, 3 moves to 1, and 4 moves to 2, right? So these are our kind of 2 starting points, and we want to now see what we could get by combining them. What other symmetries we could get by composing these 2. Okay, so we could compute the composites. So let's just do a simple thing. Maybe we simply compose one after the other. Let's see what happens. So if this one is F for flip and this is R for rotation. So if I first apply, let's say, the flip in this direction, and then a rotation, I will have to figure out the values according to these 2 tables, right? So 1 goes to 3 by the flip, and then 3 goes back to 1. So 1 will go to 1. By the flip, 2 goes to 2, and then 2 goes to 4. So eventually 2 goes to 4. Maybe I should keep the style and list the other values in the order that mappings take place. So 2 goes to 4. What about 3? 3 goes to 1 here by the flip, and then 1 goes to 3. So 3 stays the same. What about 4? 4 goes to 4, and then 4 goes to 2. So 4 goes to 2 eventually. Okay, so what is this process here? 1 is fixed, 3 is fixed, and 2 and 4 swap. This is exactly the flip along the horizontal axis, isn't it? So you see, the problem, we were trying to make a drawing which would admit the symmetry of flip along the vertical axis and 180 degree rotation, but actually but would not admit the other one, but actually it's not possible, because combining these two, just composing them, just like that, we got the other one. Now, when you, I mean, we call this 180 degrees, but when we're thinking of angles, we're usually thinking of a circle, right? So another way of modeling this whole thing would be to keep drawing circles. So imagine a Cartesian plane with a circle, right? And then it would not be difficult to show that the only possible ways you can map the circle onto itself in such a way that you preserve distance are by rotating along any degree. But now any degree will be allowed, not just 180, right? Because we have so many points now. And a flip. And so just using one flip, and it doesn't matter which axis, just one flip along one of the axes. It could also be an axis like this. And rotation is sufficient to describe all possible deformations of the circle onto itself. Okay. So this idea here that we illustrated on the kind of discrete example, we would be able to expand it also to show that even on the circle, the same works. 180-degree rotation, and the flip will give you the other flip. Yeah, so a circle will have infinitely many symmetries. This takes us back to this question where we asked whether every finite group is a group of symmetries of a certain shape. Why not asking for infinite as well, right? So let's just put finite in brackets. Yeah, so then the question is whether we want to consider infinite dimensions as well or not, but let's not go into that at this stage. Yeah, this question is something that always comes up when I talk about these things, and then I never get to think about it properly, and I also didn't bother to check the literature to what extent this question is maybe even trivial or answered or not. So if any one of you would be interested to look into this question further, please do so. Yes, there's a raised hand there. You want to say something? It's just that I can't. I think your voice might be very quiet, so that's why I might not have been able to hear you.
No, it's fine, Prof. Now, with regards to the question, and also maybe I wanted to make the comment that if we define symmetries as you define them there, then we would talk about what maybe would be referred to as maybe geometrical symmetries, whereas symmetries in general can be, if we don't consider the notion of a distance function there, we could have symmetries, but then in other context, would that make sense in the sense that, okay,
yeah,
we would define
Yes, absolutely. That's a very good point that you're making there. Here, symmetry refers to specifically preservation of distance, but distance might not be the structure you want to preserve. You might want to preserve another structure. For example, you might want to consider a linear map from a vector space to itself, which is a linear map that's a bijection. So that will be a different kind of symmetry. This will be the kind of symmetry where we are allowed to squeeze things a little bit. Like, for example, map these two vectors in such a way that angle is not necessarily preserved, and then you'll get even more symmetry. So the more general idea of symmetry is that you want to preserve something. So you have to say what you want to preserve. And when we're preserving distance, this is very much specifically, as you said, geometric symmetry in a way. But more broadly, the idea of symmetry would be preserving something. There is a lot of an important field of group theories, representation theory for groups, where you try to represent your group in a more interesting way than we achieved here. So we represented here arbitrary group as a kind of subgroup of the group of symmetries of the set, just by mapping this injectively in there. But in general, representation theory studies representing groups as similar subgroups of not symmetries on a set, in other words, bijections on a set, but maybe linear maps on a vector space, and so on. And so this way, the idea of symmetry becomes very, very kind of loose idea, and it basically becomes the idea of preservation of some structure. But not so preservation of structure in a bijective way. So you want the invertibility to stay there. Does that answer your question?
Yes, it does.
Okay, but thank you very much for that question. Okay. Okay, so let's see where we are here. So we answered this original little obstacle we had because of perhaps me not being very fresh today, but it was nice maybe that we had that obstacle so we could answer it in the end. Then yeah, so I would like us to now go a little bit into this idea of functions between groups. So there is something very special about functions between groups, not just the fact that just preservation of multiplication forces preservation of the rest of the structure. In a way, we could kind of almost like compute the entire function just by knowing what the function does, which elements of the group are mapped by the function to the identity element. So what do I mean by this? Let me first make a little introduction. So in general, if I have a function between two sets, all sorts of things can happen. So let's say I decide to map these elements to some element there, then I decide to map these two to some element there, and maybe the other three, the remaining three I map there, and then there are some leftovers, right? So the sizes of these groups, okay, so we get an equivalence relation, of course, on the domain of the function, which describes when the two elements get mapped to the same place, but the sizes of these groups can vary. They can be 2 element, 3 element, or maybe 4 element. Let me add a few more here. But when x and y are groups, and when this function preserves the group structure, which we now know reduces to just preservation of multiplication, it turns out that the sizes of these groups will always be the same. They will be bijective to each other. And it's a wonderful fact about another wonderful fact about structure preserving maps between groups. Something that's not too unfamiliar for us, for those of you who dealt with linear maps between vector spaces. You know that the kernel of a linear map kind of size of the kernel decides the size of the preimage of each vector. In fact, the reason for that is because a linear map preserves addition of a vector space, which is a group structure on a vector space. So let's prove this formulate this as a theorem and prove it. By the way, such a function is called a group homomorphism. So instead of talking about magma homomorphisms, we will now talk about group homomorphisms when these magmas are groups. They turn out to be the same thing because preservation of multiplication is enough for preservation of the rest of the structure. And so that's good. I mean, we couldn't do the same thing for monoids. We couldn't say that magma homomorphisms between monoids are monoid homomorphisms, because monoid homomorphisms also need to preserve identity elements, and magma homomorphisms might not preserve identity elements. But for groups, we can do that. And so the theorem says that given a group homomorphism, F from a group G to, maybe let's call it group X to group Y, for any two elements X and X, maybe let's call it X1 and X2 in X, the sets, actually I wanted to pick two elements in the set in the group Y. So these pre-images of these elements will turn out to be bijective. Always. Well, I mean, there is one scenario when, okay, what am I talking about here? Sorry, this needs to be elements that do come from the range of F, because otherwise we might have something that has never been mapped to. So the sets are bijective, or one of them is empty. So they're bijective whenever they're non-empty. So whenever this is not empty and the other one is also not empty, then they will be bijective. So if there's something mapping to Y1 and Y2, then these two sets will be bijective. And as a set, let me explain the notation here. F minus of Y just represents the set of those x's in X, such that F of X equals Y. Okay, so how do we prove something like this? We have two elements, Y1 and Y2. We know we have something mapping to them, X1 and X2. But now we want a bijection between the entire set of everything mapping to Y2 and everything mapping to Y1. We want to find a way of transporting back and forth between these sets in a bijective way. Any ideas? Given a random element here, let's call this element A. Given a random element A, how can we generate an element there? Let's not care about bijection yet. Let's first see if there is some meaningful way of transporting elements from this group. So those that are mapped to, not a group as said, those that are mapped to Y2 to something that maps to Y1. How can we generate from an element A? So all we know about A is that F of A equals Y2. Is it possible to create an element which now will map to, so we're looking for some kind of A prime, such that, so what should A prime be so that F of A prime will equal Y1? Any ideas? Obviously, you'll have to create this A prime out of X1, out of X2, and A, right? Anyone? So let's just try things. What would be things we could, what kind of things could we create out of the three elements x1, x2, and a? I'm emphasizing this as a fact about groups, so most likely it's not true for monoids. So we'll have to use inverses somewhere, not just multiplication, right? So how about if we go something like this, a prime equals, and now let's try to create things out of the three things. What if we try something like x1, x2, and a inverse, something like that? Where will f map that thing to? Because f preserves everything, it will map to wherever these map, right? So f will map this thing to x1 maps to y1, x2 maps to y2, and a maps to y2 as well, and a inverse will map to y2 inverse then, right? Oh, so that seems to work. This will equal indeed y1, right? Or did I do something wrong here? Well, it seems right. Okay, let's give this a try. So our function, let's call this function b for bijection. Let's define this to evaluate it at a to be equal to x1 times x2 times a inverse. Now we need to define the inverse function because we want this to be bijection, so there needs to be a way to go back, right? How can we recover back a from this expression? What can we do with this expression to get back a? So how should b of c be defined? So if I have c here, I want to be able to go back to some element there in such a way that if I started with a, I went to a prime and took it back, it would take me back to a, right? So maybe I could like try to now express a in terms of the rest. So if this was my c, right, then I would multiply my c maybe on the right side by a. No, I don't want that because then a will get cancelled. So maybe on the left side I would multiply by x minus 1, x1 minus 1, so that this cancels off. Then by x2 minus 1, so that can is taken away. And then the result will be a minus 1, but now we want its inverse to get back a. So maybe that's how the reverse should be defined. So let's declare b minus 1 of c to equal that. And now let's see if this actually works. So we have to check that b minus 1 times b minus 1 of b of a equals a. So that would be b minus 1 of b of a is this, right? And now b minus 1 of this would be x2 inverse, x1 inverse, then c. So x1, x2, a minus 1, and the whole thing minus 1, which of course is a. The fact that double inverse of an element is itself, we didn't remark it separately, but it should be kind of not difficult to see from this thing that if you swap around the roles of x and x minus 1, you get that x is inverse of x minus 1. Of course, you still need to know that inverses are unique, which we didn't explicitly prove, but we did prove it implicitly as part of another proof. Okay, so one side works. Now what about the other side? So what if I first apply b inverse to c and then apply b to it? So it'll be b of x2 minus 1, x minus 1, c. an inverse, right? And what is so it's B of the whole thing, right? And so what's that? So B of that will be x1 times x2 times whatever is inside here, the inverse of that, right? But inverse of the inverse is the same thing back, so it's just this. And opening up brackets, of course, they cancel and the x1s cancel, so we get back C. So it does work. So it was quite fascinating that a random attempt gave us a good bijection. Maybe that means that there are many other bijections as well, so that otherwise it would be strange for probability to be so low and give us exactly the correct answer. You might want to explore on your own maybe some other bijections you might find there. So we've now found two functions, b and b minus 1, which go from f minus 1 of y1 to f minus 1 of y2 and backwards. So in the forward direction, actually, our b goes in the backward direction and b inverse goes in the forward direction. And so that's how we proved that they're bijective, these two sets. So that completes this proof. Now remember that there is one special element. The special element is the identity element. So we could pick one of these to be the special elements. The inverse image of the special element of the identity element, in other words, will always be non-empty, because identity at least will always map to identity. So that kind of as an application of this theorem, you get that each of these inverse images are bijective to the inverse image of specifically one y, namely when y is equal to 1, the identity element of y. So kind of the inverse image of the identity element controls, in some sense, all other inverse images of all other elements. That's one of the fascinating things about group homomorphisms. Now, to show you that, and this is where we're going to conclude as well, to show you that the fact that we're working with a group was very important for this theorem, I'm going to give you a counterexample when the property doesn't hold if we had monoids. A very interesting monoid homomorphism is addition of natural numbers. So this thing on the left side is monoid by just adding things component-wise. You add in the first coordinate and the second coordinate. That's how you define addition there. Let's write this out. So xy plus zt equals x plus z, y plus t. And here addition is just the usual addition. So this is monoid under addition. So now, quite remarkably, the operation of addition itself, seen as a function from Cartesian product to n, turns out to be preserving addition. So let's write what this means. So in general, preservation of structure would mean that if I apply f to x plus y, I should get f of x plus f of y, right? But now my f is the addition itself, right? And x and y are pairs on this side. So it's plus applied to x1 comma x2 plus y1 comma y2, right? That should equal to plus applied to each of these separately. And if we expand the left side, so what is the sum of the pairs? Well, it's the way we define the sum of pairs. It's plus applied to x1 plus y1 comma x2 plus y2, right? And of course, plus applied to that is just adding the two coordinates. So it's this. And on the other side, applying pluses first to each of these pairs and then adding them up, we will get x1 plus x2 plus y1 plus y2. And you see that these expressions are almost the same, except that they differ in the order in which the middle terms appear. So y1 x2 versus x2 y1. And that is okay, because addition is commutative. The order can be swapped around, and associativity is also used here, of course. So addition preserves, addition as a function turns out to be a monoid homomorphism. In fact, we just proved that it's a magma homomorphism, but it's also monoid homomorphism because identity element in here. So what does it mean to preserve identity element? It means that f of 0 must equal to 0 on the other side, and identity element on this side is 0, 0, the pair 0, 0, and that equals 0 plus 0, which does equal to 0. However, natural numbers is not a group, because inverses, additive inverses do not exist here, right? And neither is this a group. And in fact, we used basically the group structure on the domain of the function for this proof. If you look at it carefully, we just use the fact that did we use just that, or a bit more than that? No, I think we just used that. We forgot to check maybe that when I apply the map to C, I do end up in this region, but that follows from the fact that this map is an inverse of the other one. And the other one, the other one has that property was checked here. Anyhow, so n cross n is not a group. You don't have additive inverses here. But now let's compute what are the sizes of these pre-images. And to do that, we're going to draw x's like this. So our positive raised this way. And now I want to draw inverse image of each natural number. So let's compute what is f minus 1 of 0. This is the set of all possible pairs x, y from n cross n, such that x plus y is 0, right? There is only one such pair. It is the set 0, 0. What about f inverse of a number n in general? This will be the set of all possible x, y's, again from n cross n, such that x plus y equals n, which we can rewrite as y equals n minus x. And then using our school mathematics, these will be straight lines with a slope of -1, right? Y equals n minus x. So this will be on its own will be f inverse of 0. This will be f inverse of 1. Then here we have f inverse of 2. Then here we have f inverse of 3. And here we have f inverse of 4, and so on. Okay, they're not quite continuous lines because we are only working with n cross n. So we only care about the digital version of the plane, right? And exactly because of that, the sets are not bijective to each other. Every time we move to the next inverse image, we get one more element in the set, right? So this example shows you that the inverse images of individual elements under this monoid homomorphism are not bijective. But of course, if we switch from n to z, then this thing will become a group, and they must be, according to this theorem. And on the picture, that just means that we will be switching to infinite lines, and then they will be bijective, because all of them will be all of them will have the cardinality of the set of natural numbers. Okay, so I think this is a good time to stop. We maybe didn't go too far into group theory, but the idea was to get an introduction to the structure of groups, and I hope that we did that. I tried to show you some of the interesting facts about groups that you encounter right at the beginning of understanding the concept of a group, but there's of course much more to come here. And the field of group theory is one of very important fields of pure mathematics. There are lots of fascinating theorems about groups, as well as the fascinating applications of groups in other areas of mathematics, and also some open problems that still haven't been resolved yet.